S. Chan presents educational video lectures. Difficult concepts made easy. Study anywhere, anytime.
Welcome to S. Chand Academy, and I am Anmol Bhatia. We are particularly learning the course Applied Thermodynamics, and the topic that we are covering in this video is air standard cycles, with a specific focus on diesel cycle and dual cycle.
If you want to study this topic in detail, refer to the book by S. Chan Publishing. Link is provided in the description box.
This is the topic which is having the specific focus on diesel cycles and the dual cycle aspect. So first and foremost, let us recall that in case of air standard cycles, we have several assumptions, and in which one of the important assumption is we have to make sure that it follows the ideal conditions, the air follows that ideal condition part. That means all those laws are applicable in terms of this ideal condition aspect. In the Otto cycle that we covered in our previous video, if you haven't watched that video, you can visit the S. Chand Academy channel's playlist. We have came across a situation in which we had constant volume process. Now, in case of the diesel cycle, we have the constant pressure process, in which you can see that there is isentropic compression. If this is a PV diagram, so you can see that from 1 to 2 you have this isentropic compression, and from 2 to 3 we are adding heat into the particular system, but this heat which is being added, that is at a constant pressure value. Then you have this isentropic expansion, and finally the heat which is coming out is having the constant volume part. So it has certain stages. The stage number 1 to 2 indicates that it has isentropic process, which is this stage. Then 2 to 3 indicates that it has constant pressure heat addition. So we are adding heat into it. 3 to 4 indicates isentropic expansion. This is isentropic expansion. And 4 to 1 indicates constant volume heat rejection. So heat which is rejected is constant volume part. So what happens, basically if I convert this PV diagram into the TS diagram, you can see that from 1 to 2, the 1 to 2 part, you are having the isentropic compression. So isentropic indicate the entropy is constant, and this axis indicates entropy. So entropy 1 to 2 is constant, and from 2 to 3 you can observe that we are adding constant pressure into it. So this line indicates a constant pressure value. This is the heat addition. Then from 3 to 4 you have this isentropic compression, in which entropy is constant, so entropy is same, and ultimately you have this volume constant part. So this is somewhat similar to the Otto cycle, in which you had the constant volume expansion, but the difference is whenever you are putting in the heat into the system and you are having constant pressures, that indicates that the cycle is a diesel cycle. Now we would be interested in finding out the thermal efficiency for the diesel cycle case. So the thermal efficiency of the diesel cycle is indicated by the same formula, which is output by input, the basic formula, and W net, as you know, is the difference in between the input and the output heat. When I solve it arithmetically, we'll get this particular formula. Now we are interested in finding out what is Q out and Q input, so that these can be substituted and a general formula can be derived. So we can see that the process 2 to 3 is having a constant pressure value. So for this constant pressure value, this first law part is applicable, in which this difference between the energy is equals to the delta E part, which is the net heat minus the work done, that is equal to the internal energy. and ultimately this W net can be obtained from the other values plus this value which is particularly for 2 to 3 case. So other values are particularly 0 here, and we have this process PdV. And we are particularly focusing on constant pressure part. So pressure is constant, we need to integrate this value of this volume. So dV's integral is V, and when we substitute it, its limit into it, we'll get this V3 minus V2 portion. And similarly, we can substitute this W net in this particular expression so that this delta U23 terms can be taken care of. So ultimately this Q input that we were interested in finding out, that can be represented as MC delta T. So MC delta T is basically an expression which is related to specific heat, but that specific heat value is particularly for the constant pressure part. So it has MCP, and delta T is concerned with the difference between the two temperatures, which is T3 and T2. So we can substitute T3 and T2 here, and an expression can be obtained. And lastly, if I talk about this output energy, so output energy's case is having a constant volume. So the same process goes along, in which you need to integrate this PdV part. Now, as I've told you that the volume is constant, so derivative of this volume would be 0. So that if it is 0, so the integral would come out to be 0 here. And the output heat is MC delta T only. It is having an expansion, so you need to undertake the negative sign into consideration. So T1 minus T4, when the negative sign goes inside this bracket, it comes out to be T4 minus T1. Substituting these values, will get this expression, which is the thermal efficiency for the diesel cycle. But this is not complete, because we are concerned with finding out an expression of in terms of R, basically the ratio. So we'll do something in order to get that converted. So we are left with T4, T1, T3, T2. I have taken this T1 outside from here and T2 outside from here, and Cp by Cv I have kept this as a constant K. Now what is this T3 by T2? So we have this expression P3 V3 over T3 equals to P2 V2 over T2, wherein P3 and P2 are equal. So on solving them, we came to a conclusion that this value T3 by T2 or V3 by V2 is equal to a constant RC, where RC is determined or defined as a cutoff ratio component, and V3 over V2 is basically related to the same aspect, that is the cutoff ratio. From this we can basically interpret that the fuel, we can say that the fuel is injected directly into the cylinder, and the cutoff ratio is related to the number of degrees that the crank is rotated during the fuel that is injected into the cylinder. So herein we are injecting the fuel at that particular part. So that injection of the fuel is particularly related to a cutoff value, that is related to the number of degrees the crank has to rotate, so that this fuel injection can be cut off. Now what is this T4 by T1? So from there on the similar grounds, this T4 by T1 can be represented as a ratio of P4 and P1. Simultaneously these processes 1 to 2 and 3 to 4 are isentropic, so I need to apply this isentropic aspect into it. So on dividing these two, we'll get this expression P4 by P1, that is V3 by V2 raised to the power R, and we have already kept this V3 by V2 as the cutoff ratio, which is RC. So on substituting these values, K we already had, T1 and T2 we had, T4 by T1 is RC, T3 by T2 is again RC. So on solving, we can get this R value, which is this compression ratio, and RC is the cutoff ratio. So on substituting this value, we'll get this final expression of the thermal efficiency, and this expression is particularly related to the diesel engines. Now we stop here for a short break. After coming back from the break, we will learn about the dual cycle and we will learn a numerical problem related to the diesel cycle. Thank you.
Now quality learning is easily available at your doorstep. S. Chand Academy brings detailed lectures based on AICTE curriculum as per the New Education Policy 2020. So do not forget to subscribe to the S. Chand Academy and access the wide world of knowledge conveniently sitting at your home. Stay connected and keep watching S. Chand Academy. Happy learning!
Welcome back to S. Chand Academy after the break, and I am Dr. Anmol Bhatia. We are learning the concept of air standard cycles, in which specifically we have learnt about the diesel cycles. Now in this part of the video, we will be learning about the numerical aspect of the same and the concept which is dual cycle. Okay, I am straight away coming to the numerical problem which is concerned with the diesel cycle. So you can see or you can read the particular numerical, and the data says that there is an engine that works on the diesel cycle in which it has an input temperature of 17 degrees Celsius. That means the inlet temperature is 17 degrees Celsius and you have a pressure value of 1 bar. So you have initial temperature pressure conditions. The pressure at the end of the adiabatic compression is 35 bar. So you have a pressure which is indicated at the end of the adiabatic compression. And the compression ratio is mentioned to as 5. So you need to find out what is the value of heat addition, rejection and the efficiency cycle. So as I've told you that the thermal efficiency is particularly related to two aspects that particularly are the input heat and the output heat values. So the first and foremost thing that we need to do from here is noting down all these parameters in symbolic form. So we have the value of a constant which is given to us as 1.4, and we have Cp values, we have Cv value and the pressure value which is 1 bar. So we need to convert it into kilopascal. Then temperature value is given to us. We make sure that this temperature, if it is in degrees Celsius, we need to convert it into Kelvin again. And we have the two pressure values because the process is having a constant pressure. So after the end of this adiabatic compression, it is mentioned 35. So that means P2 is also 35 bar. So we need to convert it into kilopascal just to maintain the uniformity. And R value is given to us, which is 5, the compression ratio. Okay, so initially we have to find out what is the value of this temperature 2, and herein we had this PV diagram that we have learned so far before going to the break, and that indicates that it has isentropic compression. Then you have the pressure part, which is constant pressure, isentropic expansion and the constant volume rejection of the heat. So T2 by T1 is equal to P2 by P1 raised to the power gamma minus 1 over gamma. That is particularly related to this particular aspect, which is isentropic process. So from there, putting in the value of P2 P1, we can find out the value of temperature, which is T2. Simultaneously, if this P4 and P3 are required for this particular aspect, so for that P4 by P3 is equal to this expansion ratio raised to the power gamma. Herein we assume that this expansion ratio is 5. Rate of expansion is same as the rate of compression. So we need to put in the value which is 5 and gamma remains the same. On solving, we'll get the value of P4. Now, as of now, we have obtained certain values. Now, we wanted T4 value. So, because T4 and T1 are concerned with constant volume processes, so we need to apply this formula, which is T4 by T1 equals to P4 by P1. So, we have the value of P4 by P1 because it is 1, and T1 value is 290 that we have calculated so far. So, we can get this T4 value. Now we got all the temperatures and pressure values. Now as the question demands that we need to find out the input heat and the output heat value. So we need to substitute the formula, which is Cp T3 minus T1. Cp, why Cp? Because this process is constant pressure process. So we substituted this formula, and before substituting this, we are not having the T3 value so far. So T3 value can be calculated easily from this isentropic expansion, and that indicates this same formula is to be used. So T3 can be obtained from there. Put in the value of T3 and T1 that we have calculated so far, and we got this value of input heat. Simultaneously, we can find out the output heat as well. So output, you can see that the output part is having the constant volume configuration. So for this, Cv T4 minus T1 can be used as a formula. So we can substitute Cv we have, and T4 and T1 we have already calculated. So from there, this portion of the output heat is determined. Now we are only left with calculating the thermal efficiency. So thermal efficiency is 1 minus the output 1 over the input 1. So on substituting these two values, we'll get this thermal efficiency aspect of the same, right? So thermal efficiency can be determined from this particular set of values. Now we will learn about the dual cycle concept in case of this thermodynamics. So far we have learned about the diesel cycle, and in our previous part of the video, which is the continued session of this video, we have learned about the Otto cycle. So Otto cycle was a constant volume cycle, and the diesel cycle was constant pressure cycle. Now if I combine both of them, I'll get a dual cycle. Likewise, you can see that in dual cycle what happens, there is a compression, which is the air gets compressed, and in the second phase we are putting in the heat into this particular system. So for some time we are putting the heat as the constant volume configuration, and when this piston moves downward, then it changes into the constant pressure heat addition process. When this particularly reaches to the bottom dead center, and when it moves upward because to reject the heat into the environment, so this heat rejection remains the same part, which is the constant volume. So herein, when we look at the pressure volume diagram, so it indicates that it has a constant volume aspect and it has a constant pressure aspect also, and we'll name it as the process, which is 2.5. We'll name this process as 1 to 2.5, 3 and 4, then 4 to 1. Let's have a look at the diagram. So 1 to 2 is the same isentropic process in which entropy is constant, and as I've told you, for some time we have this constant volume aspect. That means the volume part is constant for some time, which is 2 to 2.5, and after that particular region, when this 2.5 to 3 is there and we are inputting the heat, it becomes constant pressure. Then from 3 to 4 you can observe that you have constant entropy, and ultimately when the heat is rejected to the outside environment, it is the constant volume process. And the similar case is with the TS diagram. So for TS diagram, you can see that 1 to 2 is the process which is constant entropy process. So 1 to 2 is having the constant entropy, and then after this 2 to 2.5 you have constant volume and constant pressure representations, in which in both the aspects we are putting in the heat into the system. And 3 to 4 is the expansion process, which is again isentropic process, so entropy remains same. And from 4 to 1 you can observe that the process is constant volume when we are rejecting the heat into the surroundings. So 4 to 1 is that particular process. Now if I look at this input heat per mass, so that would be the difference between the two, which is 2.5 to 2, and 3 to 2.5, which is the enthalpy and the internal energy portion. And this is internal energy. This can be calculated by using this constant volume process, and this can be calculated by using the constant pressure process. So both of them are to be utilized here. So if we recall that previous derivations of the Otto cycle or the diesel cycle, we had used these particular formulas. Specifically, when if I talk about Otto cycle, so this was used because of the constant volume configuration. If I talk about diesel cycle, this was used because of the constant pressure configuration. Now, clubbing both of them will need to use the input value. So ultimately, whenever we want to derive the efficiency of that particular system, we need to go with the formula, which is 1 minus output by input, but we are considering per unit mass here. So this is U4 by minus U1, and this thing I have already demonstrated why we are using these two things in case of a dual cycle. So on solving, ultimately you will get, on putting in these values in terms of temperatures and pressures, you will get this particular formula of this the dual cycle. So this is 1 minus 1 over R raised to the power k minus 1 and RC raised to the power k minus 1, where RC is the ratio of these two volumes and alpha is the ratio of this pressure. Now in case of Otto cycle, if I observe that this RC value is 0, is 1, and in case of this diesel cycle, alpha is 1 because of the constant pressure part, and in case of RC, this portion is the constant volume portion. So when you particularly look at the case, in case of Otto cycle, this portion is there, and in case of diesel cycle, this particular portion is here. So from this dual cycle formula, we can easily we can easily interpret the formula of the Otto cycle and the diesel cycle. So you can particularly see that whenever I put this RC value as 1, I'll get this expression, which is 1 minus 1 over R raised to the power k minus 1. That expression is particularly for the Otto cycle. And in the other aspect, the expression would be, when I put alpha as 1, the expression would be for the diesel cycle. So this is basically the thermal efficiency related concept for the dual cycle case. Now with this, we come to the end of the video, wherein we learnt about the numerical problem of the diesel cycle, the concept of diesel cycle, and additionally we learnt about the dual cycle part. Thank you.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box. If you found our video interesting, please like, share and subscribe, and press the bell icon for future updates.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.